Hi guys, I'm Jerome Limapoy and we are discussing the discrete mathematics. Lesson 1 is topic 1, sets and relation, set and basic operation. In the introduction to set, basic set operation. Introduction to set. A set is a group of distinct and well-defined object right inside curly braces. The object in a set are called elements. Examples: set A, 1, 2, 3. Set B is a apple, banana, and orange. Union of sets. The union of sets A and B written as AUB is a set that contains element from both A, B, and without repeating any element. Example: if A 1, 2, 3 and B 1, 3, 4, 5, then AUB is 1, 2, 3, 4, 5. It combines everything for the both set. Intersection of set. The intersection of set is a B with an A. Intersection B is a set that contains only the element that are commonly to both A, B, and example: if equals 1, 2, 3 and B equals 3, 4, 5, then A intersection B is 3. It shows where both sets have in common. A complement of set. A complement of set is the complement set is written as includes all elements in the universal set that are not A. Example: if U 1, 2, 3, 4, 5 and A is 2, 4, then the complement A is 1, 3, 5. It shows what is outside of a set. Relationship under types. Reflexive relation. A relation R on a set is a reflexive of every element in A related to itself. Mathematically, for all A, in column A is in R. Example: if A is the set of people, a reflexive relation could be is related. Every person is related to himself. Symmetric relation. A relation in symmetric if whenever A and B is in R, then BA is also in R. Example: if A equals to 1, 2, then R is equal to 1, 2, 2, 1 is symmetric. It means the relation goes both ways. Transitive relation. A relation in transitive if AB and BC in R means AC is also in R. Example: if A equals 1, 2, 3 and R is 1, 2, 2, 3 and 1, 3, then R is transitive. It means the relation can be passes along. Example: let A 1, 2, 3 and R equal in 1, 2, 2, 1 and 1, 1, 2, 2. Reflexive yes is 1, 1 and 2, 2 are in R. Symmetric yes is 1, 2 and 2, 1 are both in R. Transitive is no because 1, 2 and 2, 1 are in R but 1 is missing, so you can add 1, 1 to be yes, correct answer. Lesson 1 topic 2, logic and proportional calculation. Number 1, proportion statements that are either true or false. 2, logic connectives used to combine or change proportion. Not negatives. A statement. Example: not P means not P, and true only if both P and Q are true. Example: P and Q means P and Q, or true if at least one is true. Example: P or Q means P or Q or both. Logic and proportional calculation. Example of proportion. Logic consider example involving proposition P and Q which can represent the following statements. P, it's raining, and Q, I am carrying an umbrella. P and Q, it's raining and I am carrying an umbrella. True only if both P and Q are true. P and Q, if it's raining then I'm carrying an umbrella. It's true except when it's raining and I'm not carrying an umbrella. So we're gonna add a not. Q and or P, I'm not carrying an umbrella or it's raining. True if only at least one is true. Relevance in programming and circuit design using logic rules help simplify complex condition in code or circuits. This makes this easier to read, faster, and more efficient. Example: instead of repeating checks, we group condition like card total, prime status, item count to apply discount more clearly and avoid redundancy. Proportional logic and binary operation. Proportional logic helps represent and analyze binary operation like an OR using logic, states, and connectives. Each operate is treated as proportion and the right connectives like and or shows how they interact. Logic and A and B is true only if B and B are true. Logic or A or B is true if at least one of A or B is true. This uses proportional logic to show how binary operation works. Exclusive or SOR, A SOR B is true only if exactly one of A or B is true. Implication A and implication B is false only if A is true and B is false, otherwise is true. This uses proportional logic to model binary logic clearly. Equivalence A or equivalence B is true if A and B have the same truth value, both true or both false. Lesson 1 topic 3, proof techniques. Direct proof, a method where you start with known facts and use logic step to reach the conclusion. If the premise are the true, conclusion must also be true. Example: direct proof states if a number is even then its square is even. Proof: let n equals 2k. Since n is even, then 2 squared plus equals 2k squared equals 4k squared, which is also even. Check so if n is even and n square root of 2 is also even. Proof by contrapassive to prove a statement like if P then Q, you prove if not Q then not P instead. This works because both statement means the same thing. It's usually useful when proving the original direct. It's hard. We want to prove if n2 is even, then n is even. Instead of proving directly, we use the contrapassive. If n is odd, then n square root of 2 is odd. We assume that n is odd, so it can be written as n equals to 2k plus 1, where k is integer. Now square it. N square root of 2 equals to 2k plus 1 square root of 2 equals to 4k square root of 2. 4k plus 1 equals to 2, column 2k square root of 2. 2k plus 1. This shows that n square root of 2 is odd because it in the form 2m plus 1. Therefore, the contrapassive is true, so the original statement is also be true. Proof by contradiction, assuming the opposite of what you want to prove. If the leads the contradiction, then the original statement must be true. It's usually when direct proof is hard to do. Example, proof by contradiction states there is no smallest possible rational number. Proof, assuming there is smallest one, call it r, but r/2 is also positive and smaller than r. This contradicts our assumption, so no smallest positive rational number exists. Induction step, assuming it's true for k, so 1 plus 3 plus equals plus 2 minus 1 is equals k2. Now prove it's true if it's or k plus 1, and the next old number is k square root of 2 plus 2 k plus 1 minus 1 equals k2 plus 2 plus 1 equals k2 1 square root of 2. So the statement also works for k plus 1. This complies the proof by induction. Important reminder, direct proof starts with fact and use logic to reach the conclusion. Contrapassive proof prove that if the reason is false, then the assumption must also be false. Contradiction proof that assume the opposite and show that it leads to an error or contradiction. Mathematically, induction prove it's true for the first number, then show it's true for the next number 1. IT application proof techniques. Proof techniques are used in IT to check and confirm that algorithms are correct. They help make sure the program works as expected and solve the problem properly. Algorithm valid in IT. Algorithm solves specific problems step by step. Before using them, we must make sure that we're correctly for all inputs. Correctness in IT system handle important tasks like data, security, and finance. Mistake can cause big problems. Proof techniques help make sure that programs work correctly in all situations, reducing bugs and security risks. Verifying properties in IT. Proof help check if algorithms always stop, termination, give correct result, correctness, and run efficiently. This is crucial in system where errors can cause serious problems. Complex and analysis in IT. Proofs help analyze how fast, time, and how much memory space an algorithm uses. This is important for choosing the best algorithm for a task. Formal verification in IT. Proof techniques are used to check its softwares work exactly as planned. This is very important in system where mistakes can be dangerous, like in medicine or aviation. Debugging and troubleshooting in IT. Proof techniques help find and fix bugs by checking the logic of an algorithm, step by step, making it easier to spot where the error happened. Lesson 1, Topic 4, Counting and Combination. Counting and combinatorics involves basic rules like multiplication and addition, as well as permutations and combination. These concepts are used in areas like topography, coding, theory, and probability. Practicing counting problems helps students understand how to apply this in real-world scenario, like securing data or analyzing possibilities. To create password, you choose one character at a time. Upper letter 26 choices A to Z. Lowercase letter 26 choices A to Z. Digit 10 choices 0 to 9. To find the total number of possible password, multiply the choices. 26 times 26 times 10 equals 6,760. Different password can be made. In the next scenario, you can choose one scope or two scope. For each, you have 6 flavor options. So 6 choice for single scope, 2 choice for the double scope. Total combination of equals 6 plus 2 is 8. Different ice cream orders. Addition rule ice cream. Example, you can choose either a single scope or double scope. Note both. There are 6 flavor for each. So single scope option 2, double scope option 2. Total 6 plus 2 equals 8. Combination addition rule is used when making a choice between 2 or more separate options. Just add the number of ways each can happen. Permutation, books example. Example books, you have 4 different books and want to know how many ways you can arrange them on a sheaf. Since you are arranging all 4 books, use the formula factorial n equals factorial 4 equals 4 times 3 times 2 times 1 equals 24. So there are 24 different ways to arrange the book. Formulation are used when order matters. To arrange 4 books, you have a 4 choice for the first book, 3 for the second, 2 for the third, and 1 for the last. Multiply 4 times 3 times 2 times 1 is equal to 24 ways to arrange the books. You have 7 members and you want to choose 3 for a committee. Since the order doesn't matter, this combination will use the formula C. Combination of n r is equal to n factorial divided by r factorial is times n minus r factorial. Combination of 7 r and 3 is equal to 7 factorial divided 3 factorial times 7 minus 3 factorial is equal to 35. There are 35 different ways to choose 3 members for 7. Combinatrix helps in psychotopography by showing how many ways letters or symbols can be arranged or replaced to create source codes. For example, in a substitute cipher, each letter is replaced with another. Combinatrix helps us to count how many different ways this can be done, making it harder for the others to crack the code. Attack analysis, it helps estimate how many possible keys exist, making it easier to find weak spot in encryption. Block ciphers used in system like AES where data is shuffled permitted. Combinatrix ensures their shuffles are secure and efficiency. Combinatrix encoding theory, error correcting codes, it helps create codes like Hamming or Reed-Solomon that can detect and fix error in data during the transmission or storage. Combinatrix encode theory, Hamming distant measure have different codes are more distant means better error detection and more. Combinatrix optimization helps find the most like original message by efficiently correcting errors in receiving data. Combinatrix in probability theory, Combinatrix helps count possible outcomes using formulation and combination, making it easier to calculate the probability of event in situation involving chance or randomness.